Okay, my presentation is same as the previous presentation. I mean, the content is same, but the way is the method that we apply is different. I want to talk about the observing strategy for electromagnetic follow-up of gravitational wave events. Before that, we explore different observing scenario. Let's talk about the challenges for these observations. As you can see here, in this plot, it shows that typically the gravitational wave events have a large sky localization uncertainty. It means that to find a kilonova or electromagnetic counterpart, you should search a wide range of the sky. For example, for GW 900425, the 90% of the area is around 7,000 degree power 2. It means that if you have a telescope with 1 degree power 2 field of view, you need 1,000 fields to cover this area. And another challenge is that the nature of the electromagnetic counterparts that is faint and become fainter very fast. As you can see here is an event like GW70 or 817 in different filters, and as you can see, the peak of the light curve is less than 20, and over the time it's become faint very fast. And it's for events like GW70 or 817 at 1 gigaparsec. The peak of the magnitude is around 22, less than, and is based on the different filter, and it goes down over the time very fast. So it means to have a successful observations, it's necessary that we present an optimal observing strategy. To give an optimal observing strategy, we classify telescopes into categories. The telescopes with narrow field of view, I mean the telescopes if have a less than 1 degree power 2 size of the field of view, we use the galaxy targeting strategy. And typically it means that the telescope can observe single galaxy per pointing. And for telescopes with wide field of view, I mean the field of view larger than 1 degree power 2, we apply the tiling strategy, and it's typically we can observe a few or several galaxies per pointing like this. Now, for two next slides, I will focus on the search strategy for narrow field telescopes. As I said, we use the galaxy targeting method. We use a galaxy cross matching within the volume, and we use a Gray plus galaxy catalog. It means that we find the galaxies that are located within the 3D sky localization of the gravitational wave. So these galaxies are a host galaxy candidate. It means that we should observe this galaxy to find the host galaxy of the gravitational wave, or I mean the host galaxy that we can find the electromagnetic counterpart. But typically when we do the galaxy cross matching, the number of the galaxies that we should observe is from 100 to 1,000 galaxies. So it's not an efficient way that we observe all of these galaxies. So we use the ranking method. It means that we can rank the galaxies based on the characteristics of these galaxies. And so we can determine that which galaxies are important for us, that we start the observation for this galaxy. For example, we can rank based on the mass or based on the 3D GW sky localization, that is the probability density. Now I want to talk about the search strategy for wide field telescopes, and to last slide, I just focus on this strategy. At first, we should create a sky grid. For example, you consider a sky as a sphere, and we fix this blue point shows the center of the field of view of the telescopes. So at first we fix this, the center of the field of view of the telescopes, and based on the size and shape of the telescopes, we create the tiling pattern like this. For example, it's for the telescopes that have a shape of the rectangular. in our project, when, for example, you consider this is a sky localization of the gravitational event, we consider 90% of to the sky localization, and we generate the tiles. We generate the tiles that it's cover the region of the 90% of the 2D sky localization, and also it covers the galaxy cross, the host galaxy candidate that they determine based on the galaxy cross matching within the volume. So as you can see here, the tiling covers this area. And now we rank the tiles based on the 2D sky localization of the gravitational wave and based on the characteristics of the host galaxy candidate. So we determine that which stars are important for us, that we start the observation for which stars. For example, is an example of our ranking method for a simulation of the gravitational wave during O4 and for a sky localization larger than 100 degree power 2. As you can see here, the 2D sky localization is the best ranking method if we compare to the characters of the host galaxy candidate. And it shows that just by observing 125 tiles that they are ranked based on the pixel ranking, we can identify the tiles that contain the electromagnetic counterpart with the 80%. Okay, now I take some example for an event that are well localized. For example, if you consider this event that have an area with 30.5 degree power 2 and the volume is 0.50 10 power 5 cube megaparsec, we generate the tiles that cover 2D sky localization 90%, and also discover the galaxy. I mean, the black circle shows the host galaxy candidate. If we want to observe based on the ranking method, we can observe and we start from the tiles that are ranked. In the 10th tiles contain the electromagnetic counterpart, and if we rank based on the characteristics of the host galaxy candidate, 13th and 12th of the tiles contains the host galaxy, contains the electromagnetic counterpart, the gravitational wave sources. So it's not necessary that we observe all of the tiles. Just based on the ranking tiles, we can catch the electromagnetic counterpart very fast. And now I want to give an example for wide localization event. For example, you consider this is a 2D sky localization of the event, that the number of the tiles that we should observe to catch the electromagnetic counterpart, they cover this area, and the host galaxy candidate is around the 1,000 tiles. But if we start observation based on the rank tiles, based on the ranking methods, we can catch the tiles that have the electromagnetic that contain the electromagnetic counterpart of the gravitational wave at the first tiles. And if we rank the tiles based on the 2D gravitational wave localization, we can find the tiles that are placed in the 6th rank place. We can catch the gravitational wave source. So it shows that it's not necessary that we observe all 1,000 tiles. And ranking, oh my God, sorry. A ranking method can help us to catch the tiles very fast. Okay, now I want to give it as a case study for electromagnetic observing strategy. I want to talk about the 7-dimensional telescope. This telescope is I take here as an example that's how we can do the observations for ground-based network telescope, and we apply the optimal observing method. Seven-dimensional telescopes is a network of the telescope that made of the 20 telescopes. And we call this 7DT because these telescopes, this network of the telescope can observe right ascension, declination, and distance is 3-dimension, flux, radial velocity, and the wavelength, and the time. For this reason, we call this 7-dimensional telescope. Field of view of one of these telescopes is 1.2 degree power 2. But if these telescopes observe different part of the sky, they can observe, they can cover about 24 degree power 2 of the sky. And it's equipped with a 40 million bands filter, and it can do low resolution spectra. And also it's equipped with broadband filter, U, G, R, I, and Z. Is under construction with GW University, Seoul National University, and we hope that it will be complete for the phase 2 runs of the 04 of LVK, and is also located on the Chile. For this telescope, we can apply different method. We can apply deep observing models. It means that all telescopes observe just a part of the sky. So its field of view is 1.2 degree power 2. And if all telescopes of the different part of the sky is a wide observing mode, and it can cover 24 degree power 2, or we can do the observation between deep mode and wide mode. That for the next slide, I will talk about that we work in the between, and how mode we should determine for observation depends on that we expect that the kilonova is bright or faint, and how many stars we have to observe. For example, for these events, the number of the stars that we should observe to catch the electromagnetic counterpart is around 26. But the result of the simulation shows that if we just observe 55% of the stars, we can catch the electromagnetic counterpart with 80%. So it means just observe 14 stars is enough. How we do observations? We have a 20 telescope. We set one telescope at first in the 40 stars that are more important for us based on the ranking method, and remains 6 telescopes. And then we set the other telescopes in the 6 stars that are more important for us. So the orange color shows that these stars are observed with the 2 telescopes. And the yellow stars shows that these stars observed with the 1 telescopes. And based on the ranking method, we can catch the electromagnetic counterpart with the stars that are placed in the rank 2. It's finished. Okay, I overview about the electromagnetic strategy that we apply for narrow field telescope galaxy targeting method, and for wide field telescope tiling observations, and how we generate the stars and how we rank the stars is is in this GitHub, but is not public yet. When we publish our result of the simulation, we become this GitHub public, and the name of this code is Jack Worcester. And thank you.